In our oscillations chapter, we are going to study a very specific type of oscillatory motion, namely simple harmonic motion. Simple harmonic motion is a very specific type of oscillation. It has a very specific mathematical structure that goes with it. We're going to cover that in this unit. But the first thing that we need to recognize about this type of motion is that it only occurs when you have a restoring force that is linear with respect to the position of the object that is oscillating. And we've seen this force. That's our Hooke's law spring force down here, which I'll get to more in a moment. The negative, if you recall, in Hooke's law, meant that we had a restoring force. So it was always trying to bring the mass back to the origin. The spring, when it was stretched, would pull the mass back to x equals 0. And when it was compressed, it would also try to push the object back to x equals 0. So the first thing that I want to focus on, that I would like you to kind of lock in on here, is my exploded statement over here. So please get this bit down into your notes. That any linear force that has a negative slope gives us simple harmonic motion. As soon as you see that negative slope, linear force, you know you are dealing with an object that will be undergoing simple harmonic motion if released and let oscillate without any friction or applied forces to bring it to a stop. So the spring force will be the first one that we study and the most important one. The block on the end of the spring, as we see here, we have the block on the end of a spring. When we pull it, it wants to restore back to the origin. Will absolutely be our primary focus. It'll be our prototypical system that will map out the basic mathematics that will extend and use to understand other systems. And the block on the end of the spring is called a block oscillator. So that's other language that we are going to use. Now, another important oscillatory system, and the block oscillator is the primary system, but the next most important one for us in this unit is going to be the simple pendulum. And please get into your notes that by simple pendulum, we are referring to the fact that we have a point particle mass, not a sphere, not a ball, point particle mass at the end of a massless string. So we're not considering any weight or any aerodynamics, anything going on with the string. And let's take a look real quick here to see where our linear restoring force comes from, because it doesn't appear to be linear. And we're going to see this again later in the chapter, so I want to introduce it and get you thinking in that direction. So we have mg pointing straight down, and we have a tension force T, or F sub T, pointing along the string upward in this case. And those are the only two forces that act on the simple pendulum. Well, if we consider the mg force broken down into an mg cosine theta and mg sine theta, where the angle theta is here. So the angle theta in your notes translates down here. So we have our mg sine theta. I'll do it in blue to highlight it. The mg sine theta here is our mg sine theta here. So this is actually the restoring part of mg that wants to restore the pendulum back to its x equals 0 position at the bottom. Well, we can see that that is not linear. It's a sine function. But we will see in our notes and coming pages of notes that we're going to be able to replace that sine function with just theta at very small angles. So we'll go through this in a little more detail. But again, I wanted to kind of get your neurons shifting in this direction, that even if we have a nonlinear force, if there are regions or approximations that can be made such that the nonlinearity goes away under certain conditions, then we can achieve simple harmonic motion even then. So I realize it's a relatively short discussion on this first page, but I'm going to zoom out here. I'm going to clear off some of my markings for you and let you get down the annotations on this page, and I think it gives us a good starting point.